So here we're looking at an adapted version of the first worksheet for our parametric equation study. And so the idea is we've got a baseball that's been hit and it's at a height of 3 feet above home plate. That's 0, 0. So the ground is not at a height 0. That's the height 0 is actually 3 feet above the ground when the bat makes contact with the ball. And so then we've got this vector that represents the initial velocity of the ball. And so as we see, the ball is going to take off, but it's not going to be able to stay on that trajectory of the initial vector because, of course, gravity is acting on the ball. So it's going to start to come back down. But in the initial stages, we've got this initial velocity is at 100 feet per second the moment it hits leaves the bat, and it's at an angle of 60 degrees. So in the first question, we're asked to write the vertical and horizontal components of the ball's velocity just as a result of the impact of the bat. So in the x direction, we've got this, if we kind of drop a perpendicular down, so we've got this x and these y components of this velocity of 100 feet per second. Well, if we want to just isolate the x component of this vector, well, that's going to be 100 times the cosine of 60 degrees. So we're just trying to find the horizontal side of this right triangle, so the x component of our vector. And then likewise, for the y component of our velocity vector, that's going to be 100 times the sine of 60 degrees. So those are the velocities in the horizontal and vertical direction of the ball as it leaves the bat. So now from this information, along with factoring in gravity for the vertical direction, we want to start to write a set of parametric equations that are describing the position of the ball at a particular time after it's left the bat. So in the horizontal direction, there's no gravity acting on it. We're told that we're going to neglect any kind of air resistance or anything. So the only thing that's affecting the flight of the ball is that initial velocity as a result of the ball being hit. So our equation, a parametric equation in the x direction, is going to be 100 times the cosine of 60, or if we were to multiply that out, that equals 50. So it's going to be 50t. So that's our parametric equation for the x direction for the ball. In question number 3, we're asked for the parametric equation in the y direction for the ball. But of course, in the y direction, we don't just have that initial velocity factoring in. We also have gravity. And so the way gravity is going to be represented is with a negative 16t squared. So as more time goes by, because of that squared variable, it's going to have a greater and greater impact. It's going to overwhelm the initial velocity, and that's what models the idea of the ball coming back down to Earth. So our equation in the y direction is we have the positive, and it's that 100 times the sine of 60, which, if we were to push buttons on our calculator, was 86.6. So we have that positive 86.6t, since that's going upwards, but then we have to subtract the impact of gravity, which is that 16t squared going down. And so then once we've got those two equations, we've got the x and y position of the ball tied to a particular time, the time since it's left the bat. And so we can actually graph these parametric equations, sets of parametric equations, on our graphing calculators. Down below, I already have the graph of the equation. We can see it's a parabolic function. And so I did this on Desmos, but you can do this on your graphing calculator. And so you just need to make sure that you put it into parametric mode, that we're not graphing it as a function. We don't just have x's and y's, or f of x and x. We have an x equation in terms of t and a y equation in terms of t. And so the way we access parametric mode in the two different types of calculators. You can see there the set of button clicks for the Inspire. So you got to get into the graphing menu on the Inspire. You then hit the menu button, and then within that menu set of options, you choose the graph entry edit. And so there you'll see a whole list of different types of equations that you can use. And so what we want to choose is parametric. And so then once you choose parametric, you'll see that it'll pull up an x1 of t equation, a y1 of t equation, and then there will be some additional information about how you want to set up the limits on the parameter t. For the older models of calculator, we're going to start off while we're just in regular calculator mode, not like in graphing mode or anything like that. So we're going to hit the mode button, and then you've got to look down in that screen to find the row about 4 or 5 rows down in the display where normally we're graphing in function mode. But we want to change it so that it's in parametric, so that's the par there that I have bolded. And then there's a couple other modes that we don't need right now. We hit the enter button, and then if we hit the y equals key up at the top of our calculator, now we'll see that it doesn't say y equals. It'll instead be giving us a set of x and y equations into which we can enter our 2 parametric equations. So we've got one of them here, that's the y equals 86.6t minus 16t squared, and the other one, if you'll recall, was 50t. And so if we enter those, and then we just have to adjust our window to make sure that our graph fits, and so we have experience with that from graphing just regular functions. But if you hit the window button on the older calculator, or go to the menu and then work through the set of options to adjust the display on the Inspire, we can see in the y direction we're topping out at a little bit less than 125. In the x direction we're at a little bit more than 250. And then we can just leave the t values to be kind of at their default, and we should be okay with our graph. And so we're asked next to find graphically the approximate time and place at which the ball is back to y equals 0. So when it's back not to the ground, because remember y equals 0 corresponded to the height of the ball when it was hit, which was 3 feet above the ground. And so in other types of functions, we would use the intersect tool to help us out. But the intersect tool does not work for us when we are in parametric mode. So it's not like we could graph a horizontal line and then use the zero tool or use the intersect tool to try to help us out. We're going to have to do it algebraically. We can kind of eyeball it on the graph a little bit if we want to, as best as we can. We can see that it's going to be a little bit more than like, a little bit less than 250 feet. As we saw in the graph. But if we wanted to actually calculate it, we would have to plug in 0 in place of y in our y parametric equation. So if we go 0 equals 86.6 t minus 16 t squared. So here we have a quadratic equation, so we can see that we can solve this by factoring out a t. So if we do that, we've got t times 86.6 minus 16t. And so now we can set each of these factors equal to 0. So obviously one of those answers is going to be t equals 0. The moment the ball is hit is when it starts off at that height. And then the other time is going to be found by setting this factor equal to 0. So we go 0 equals 86.6 minus 16t. I can add 16t to both sides, and then divide both sides by 16, and we get an answer of 5.41 seconds. So it'll be 5.41 seconds after the ball initially hit the bat that it'll return to that height of 3 feet above the ground, which corresponds to that y equals 0, the way the problem was initially set up. Now, if we want to find the time that the ball actually hits the ground, well, now we're going to have to replace 0 with -3. So, or a y with -3 instead of with 0. So if we do the same thing, we've got -3 equals 86.6t minus 16t squared. So this time we're not quite as fortunate where we already have the equation equal to 0 like we did here, so we could just factor right away. Instead, we're going to have to move everything to one side of the equation and then factor, or in this case, use the quadratic formula in order to solve. So I'm going to move everything over to the left-hand side. So we're going to end up with 16t squared minus 86.6t minus 3 equals 0. And so now that's the equation that we need to solve in order to figure out at what time the ball will actually hit the ground, as opposed to returning back to the same height as where it started when it left the bat. So we're going to have to use the quadratic formula, because that's certainly not going to be a factorable expression. And so if we set that up, if we recall our quadratic formula, negative b, so b is negative 86.6, so we're going to have a positive 86.6 plus or minus, and we'll deal with how we're getting two answers for this, and I'll talk about that in just a moment. But plus or minus the square root of b squared, so 86.6 squared, minus 4 times a, so 16, times c, which is negative 3. And then that's all over 2 times a, or 2 times 16. So as you can see, we're going to end up with two answers by the time we're all said and done here. Well, one of those answers doesn't make sense with the context of the problem. If we think of this as being t equals 0 right here, and then we're looking for that time when it hits the ground at a height of negative 3, well, the other answer that we're going to get is going to be for when it would have hit the ground before it been at the ground, before it made contact with the bat. So that answer just doesn't make sense with the context of the question. So really that means that we can just ignore the minus part of the equation and just include the positive part. So if we number crunch everything that's underneath the square root symbol, take the square root, add 86.6, divide all of that by 2 times 16 by 32, we'll find that our time at which we're going to hit the ground is going to be just a little bit later, 5.45 seconds compared to the 5.41 seconds, which makes sense. It shouldn't be a terribly long period of time for it to fall that last 3 feet. And then finally, to close things out, we want to know what's the horizontal distance that the ball has traveled. So we can take this value that we just got, this 5.45 seconds, and we can plug that into our x equation. Recall that that was 50 times t, so I can go 50 times 5.45 seconds. And remember the units on that 50, we didn't write it in earlier, but that was in feet per second. That goes back to the initial speed coming off the bat. So if we multiply a speed times an amount of time, we're going to get a distance. And so in the end, 50 times 5.45 yields a distance of 272.3 feet. So that's the horizontal distance that the ball will travel. So again, we just have here another example of how we can use parametric equations to provide that extra layer of context, not just track the horizontal and vertical position of the ball, but also to keep track of the length of time that the ball is traveling in the air, when is it going to hit the ground, etc.